Satellites are typically powered by solar energy, as it is the most common and reliable source of power available in space. Here's an overview of how satellites are powered. Solar panels. Satellites are equipped with solar panels that consist of arrays of photovoltaic cells. These cells convert sunlight directly into electricity. The solar panels are designed to efficiently capture and convert as much sunlight as possible. They are usually positioned on the satellite's body or deployed as wings or panels that can be angled towards the sun to maximize exposure. Power regulation and distribution. The electricity generated by the solar panels is regulated and distributed throughout the satellite using power management systems. These systems ensure that the power generated is at the appropriate voltage levels and is distributed to the different subsystems and payloads as needed. Power storage. Satellites require energy storage systems to provide power during periods when they are in Earth's shadow or experiencing eclipses. Rechargeable batteries are commonly used to store excess power generated by the solar panels. The batteries are charged during periods of sunlight and discharge their stored energy when the satellite is not receiving direct sunlight. Power management and control. To efficiently manage the power usage and ensure the satellite systems operate within power limitations, satellites employ power management and control systems. These systems monitor and regulate the power flow, prioritize power allocation to critical subsystems, and optimize energy consumption to maximize operational efficiency. It's worth noting that some specialized satellites, such as those on deep space missions, may use alternative power sources in addition to or instead of solar power. These can include radioisotope thermoelectric generators, RTGs, that convert the heat generated by the decay of radioactive isotopes into electricity. However, solar power remains the primary and most widely used method for powering satellites in Earth orbit. By harnessing solar energy and efficiently managing and storing power, satellites can operate for extended periods in space, performing their intended missions and transmitting data back to Earth. The power consumption of a satellite can vary depending on its size, purpose, and the specific systems and payloads it carries. Satellites are designed to operate within strict power constraints and maximize energy efficiency due to the limited availability of power sources in space. Here are some general considerations regarding the power consumption of satellites. Communication satellites. Communication satellites, which provide various services like television broadcasting, internet connectivity, and telecommunication, typically have power consumption in the range of several kilowatts to tens of kilowatts. The power is primarily consumed by the satellite's communication systems, including transponders, amplifiers, signal processing, and data transmission equipment. Earth observation satellites. Satellites used for Earth observation, remote sensing, and imaging applications have varying power consumption depending on their sensor systems. These satellites utilize power for imaging sensors, data processing, onboard instruments, and communication systems. Power consumption can range from several hundred watts to a few kilowatts. Navigation satellites. Navigation satellite systems like GPS, Global Positioning System, satellites require power for signal generation, atomic clocks, and onboard transmitters. The power consumption of navigation satellites is typically in the range of a few hundred watts. Scientific satellites. Scientific satellites designed for specific research purposes, such as studying the Earth's atmosphere, climate, or space phenomena, may have diverse power requirements. Power consumption can vary from tens to hundreds of watts, depending on the instruments and scientific payloads carried on board. It is important to note that these power consumption estimates are generalizations, and actual values can vary significantly depending on the specific design, mission requirements, and technological advancements of each satellite. Satellite manufacturers and operators continuously strive to optimize power consumption, maximize efficiency, and prolong the operational lifespan of satellites in space. Satellites primarily rely on solar power for their energy needs, as solar panels convert sunlight into electricity to power various systems and payloads. Communication satellites, which enable television broadcasting, internet connectivity, and telecommunication services, typically consume several kilowatts to tens of kilowatts of power. Earth observation satellites used for remote sensing and imaging applications consume power ranging from several hundred watts to a few kilowatts. Navigation satellites, such as those used in GPS systems, generally require a few hundred watts of power for signal generation, atomic clocks, and on-board transmitters. Scientific satellites designed for research purposes, like studying the Earth's atmosphere or space phenomena, can have power consumption ranging from tens to hundreds of watts. Satellites employ power management systems to regulate and distribute electricity generated by solar panels, ensuring it is at the appropriate voltage levels for various subsystems and payloads. To provide power during periods of eclipse or reduced sunlight, satellites incorporate rechargeable battery systems to store excess energy generated by the solar panels. Power management and control systems are implemented to efficiently manage power usage, prioritize power allocation, and optimize energy consumption to maximize operational efficiency. Satellites are designed to operate within strict power constraints due to the limited availability of energy sources in space, and energy efficiency is a crucial consideration in satellite design. While solar power is the primary power source for satellites, some specialized satellites on deep space missions may use alternative power sources, such as radioisotope thermoelectric generators, RTGs, that convert heat from radioactive decay into electricity. These facts provide an overview of the power consumption and management aspects of satellites, highlighting their reliance on solar energy and the need for efficient power systems in space.